Dear participants, hello everyone. I hope everyone is feeling well after yesterday's party. And now we are starting our school and our first lecture by Professor Naumov.
Thank you. Good morning, everybody. So let's begin. So I'm going to give you two lectures on particle physics. This will be a very introductory introduction. So let me begin with unit conventions. This is important that we are on the same page. So in high energy physics, usually we place Planck constant equal to the speed of light equal to 1, and then energy and mass has the same dimension of mass, and this is inversely proportional to the dimension of length and time. Therefore, usual relationship between energy, momentum, and mass is now reading like that. Energy squared equals to free momentum squared plus mass squared. The wavelength is 2 pi divided by the momentum. And time is just reciprocal to energy. If you want to come back to your usual world with meters, kilograms, and so on, then there is this set of unit conversions, like 1 equals to the product of h bar and c, and this is equal to around 200 MeV times Fermi, where Fermi is, femtometer is 10 to the minus 13 centimeters. And this allows you to convert from, say, inverse energy, GV, to femtometer, and backward, and between seconds and inverse GV. GV is giga electron volt. Now, let me use this small piece of information for something useful. Let's discuss the question why momentum and coordinate are not equal experimentally, that we cannot get a good accuracy in the measurement of coordinate while we can get a good accuracy in measurement of momentum. This is again based just on these numbers which I highlighted. So we begin with the Heisenberg uncertainty equation. So the dispersion in the coordinate times dispersion in the momentum is larger than h over 2, or when h bar equals to 1, this is larger than 1/2. Then let me introduce a dimensionless relative dispersion of momentum, epsilon, which is just a ratio of dispersion of momentum divided by momentum. This is something which experimentalists deal with in their detectors, so they want to have this value as precise as 1% or something like that. And then we just rewrite this Heisenberg uncertainty using the conversion unit from the previous slide to write the following formula. The dispersion in coordinate is larger than 1 over 2 dispersion in the momentum, where we go to the relative dispersion and times momentum, and we get this numerical value here. And this is important because this means that if you have a detector which carefully measures a momentum with a relative precision of 1%, and the momentum of your particle is about 1 giga electron volt, then the uncertainty in the coordinate is larger than 10 femtometers. What does this mean? The best experimental resolution in the coordinate is something like 1 micron. So you're using silicon cheap detectors, and 1 micron is much, much larger than the uncertainty which we just estimated. So when you have a detector which measures momentum with 10 to the minus 2 precision or 1% precision, you basically have the digit on your ruler, which is way, way larger than a typical spatial dimension of your wave packet of a particle. Therefore, experimentally, detectors measure carefully momenta and not accurately the coordinate. Now let us dive in a simplified way into organization of matter. So if we take a piece of cheese, its typical size is about 1 centimeter. If we go deeper, it is constructed in molecules. on the scale of 10 to the minus 7 centimeters. Each molecule is made of atoms, which is order of magnitude smaller than a molecule, and 100,000 times smaller inside an atom you can find a nucleus, which consists of protons and neutrons, and finally, proton and neutron consist of quarks. These are most fundamental objects the matter is made of. And based just on this simple picture, we can construct a full zoo of particles. In total, we have 118 chemical elements in the periodic table and more than 3,000 of different isotopes. And lots of these isotopes are unstable, and they decay via alpha, beta, or gamma decay ways, or via spontaneous fission, and there are other processes like neutron capture. Now let's go to fundamental objects the matter is constructed of. So all known matter is made of a number of just fundamental particles. And fundamental particles are indivisible in terms of the framework of the modern theory. And there are two classes of these particles. One is the fermion, which has the half-integer spin. It can be 1/2 of, I restore here for a moment the Planck scale, so 1/2 of the Planck scale or 3/2 of the Planck scale. Or it can be boson, which can be 0, 1, and 2, and so on, of H bar. The standard model, which is the most general theory, which is the most successful theory describing our world, is consisting of different fields. I will talk about this later. But if it's still on the page with particles, then its contents is the following. So it has quarks, which are grouped in 3 families: up and down, charm and strange, top and bottom. And each of these family has 3 copies because of different QCD color, which is just another name for charge of the strong interaction. And the second family is lepton. It is also organized in a group of 3 doublets with electrons and charged leptons. So electron, neutrino, and electron, muon, neutrino, and muon, tau, neutrino, and tau lepton. And the third group of particles or fields is so-called interaction carriers. So these are particles or fields which carry the interaction between these species here. These are gamma or electromagnetic quantum, W plus and minus boson, Z boson, 8 gluons, which also carry charge and anti-charge, and a Higgs boson, without which a standard model would be incomplete. On top of that, almost all of these particles have their antiparticles. And their antiparticles are the particles with the same masses, with the same spin, and with the opposite electric charge and opposite color. So some examples are electron and its antiparticle is positron, antiparticle to proton is antiproton, and antiparticle to neutron is antineutron. All these particles actually do exist. Now let's talk about fermions and bosons. So fermions, as I said, is a half-integer spin, and they obey the Fermi-Dirac statistics, which means that if you have 2 fermions with the same quantum numbers, like spin aligned in the same direction, then they cannot occupy the same space. So it is depicted here in this nice cartoon drawn for me by Marina, who is making pictures. Marina, are you around somewhere? I don't see her. Okay. Okay. So this means that some room is already occupied by another fermion, so a fermion cannot enter if it has the same quantum numbers. But what is more remarkable, if you go deeper and try to classify this with the group theory, a mathematical framework which describes the most topological things, then one can realize that SU2 group, which describes the spin of a fermion, is actually, in a sense, identical. I'm saying this not in a very accurate mathematical way, but this is identical to a Möbius strip group. Therefore, we can say that we are all many-sheet Möbius strips inside, so because we are all made of matter, which are fermions. So now live with that, Möbius strips. Bosons are particles which have integer spin, as I said, and in the standard model we have those bosons which I already mentioned. And regarding the leptons, so we have charged leptons, as I said, and neutrinos. Neutrinos are having zero electric charge, and they do not participate in the electromagnetic interactions. So what is remarkable about quarks is that their charge is fractional of the electron charge. So it can be 2/3 of the electron charge or minus 1/3 of that charge, and vice versa for antiquarks. And one can construct different bound states out of these quarks. So the typical bound state, which we all find in nature, it consists of free quarks, and known examples are proton, neutron, or lambda hyperon, or some other sigma hyperon. So there are some families with these free quarks. And another family consists of quark and antiquark, and these are known as mesons. Examples are pion and kaon. So regarding the gauge bosons, I will explain on the next lecture why they are called gauge. So far, just if you are not familiar with, just keep this in mind. So let me explain this in some more detail. So gamma is a quantum electromagnetic field, so it is actually responsible for the electromagnetic interaction, and it couples to electric charge. Gluon, 8 gluons, they are responsible for the strong interactions between quarks, and they are coupled to color. Color is just a fancy name to say charge, but so charge is already occupied by the electric charge, and so we call it color, but actually it is a charge. And also W and Z, these are massive bosons, which are responsible for weak interactions. And they are also charging to some weak charges. And the Higgs boson is a kind of an outstanding particle. It has zero spin, and this is the only known fundamental scalar in the world. So all other scalar particles are composite particles, and this is the only fundamental one. Usually, one can ask a question if Higgs exchange by Higgs boson also is a kind of force, a thief force. It is actually, can be considered like that, but it is not a thief force in a sense of gauge invariance or gauge interactions. I will explain this later, next lecture. Okay, now let's go to the next chapter, is particles and fields. So far, we were discussing particles, and you might get an idea that these are kind of small balls. Actually, it is not. It is very far away from this naive picture. What we call particles is just an excitation of a field. But before that, we have to understand what the field is. And so let me begin with this very mechanical model. I take just a mattress consisting of springs which are tied together, and so they are they have some frequencies of how to say, of oscillations, right? Thank you. Okay, so while it is looping this movie, I will slowly explain what it is showing. So if you take this mattress, then you can calculate this just from mechanical point of view. So you can find the equation of motions of each of these springs. You can solve this equation of motion. And when there are many springs like that, then when you are doing the solution, you will realize that it is much easier to solve, instead of solving a system of coupled equations like that, where different indices depend on other indices, it is much more convenient to make so-called diagonalization when this equation of motions are independent. And this diagonalization is just a mathematical method, and it produces so-called normal modes. So normal modes are modes when the entire structure oscillates and the equations for this entire structure are independent. And each normal mode has its own way to oscillate, spatially, and also it has own frequency. So now I think you understand everything. So these are the frequencies of oscillation. So they have two labels, m and n. These are just integer numbers. And now you can see this very fancy way of oscillations. So you can see this fancy way of oscillations. It can oscillate as a whole structure, or it can be oscillating like that, like another way, and so on and so forth. So all these are just normal oscillations. And now, in the end of this animation, you will see that in the limit, when the number of oscillators is infinitely large, you get something very smooth. And this is something very smooth, is what we call actually a field. And when we add some quantum rules to that, this field becomes quantum field. So in the end, yeah, here we are. This is the field, and in the center of this field, you have what we call particle in our usual sense. So particle is just an excitation of a field, and the field is just a limit of this mechanical system when the number of springs goes to the infinite number. To be more precise, what we are doing, so for every coordinate of each oscillator, which depends on time, we just replace this by a function, which is the field, which depends on three-dimensional coordinate. And this three-dimensional coordinate is associated with the number, integer number of this particular spring, when you have in the position of x a certain number of springs, and time. And when you take a limit, the number of springs go to the infinity, difference between, space difference between two springs goes to 0, but the product n times a is fixed, then you get a field. So this is the definition of a field. And as I said, in quantum world, you just quantize this field, which means that you introduce operators, so creation and annihilation operators, and this way you produce a kind of a particle. For example, this definition here, square root of two energies multiplied by a creation operator acting on a vacuum state, the state with no particles, produces you a particle with definite momentum. So the vacuum state is the zero particle state. So it is not empty space. In quantum field theory, vacuum is not empty. It is just zero particles. And so then adding interactions, it can destroy, create, and transform this field excitation to each other. And I'm not going to show you many equations. So I will just show these three equations here because they are kind of fundamental, and I just want them that you at least know this equation. So each field, so we have in general three different fields. One is scalar, which means that it has zero spin. And this field obeys an equation which is called Klein-Fock-Gordon equation. So on the West, it is usually called just Klein-Gordon. We add Fock because actually a Russian or Soviet physicist was the first who discovered this equation. And so this is the free equation, and its solution is just that. So it's just a linear combination of plane waves with creation operation and annihilation operators. Then there is a brilliant equation which describes spin 1/2. This equation is named after Dirac, and this is the solution of this equation. And finally, we have a particle with spin 1, or we call it vector particle, and the equation, which it obeys, is Maxwell equation. So now when we understand that particles are excitations of a field, we can dive deeper, and this is how our universe actually looks like. So everything we are made of, universe, star, planets, cats, phones, whatsoever, so all matter around, and even not a matter, consist of quantum fields which are filling the universe. This is an animation shown here. So all these fields just stack around. They are vibrating, and their vibrations is transferred between each other, and this is the way how we describe the interaction. So all our universe is filled with this quantum field. So actually, if you want a qualitative picture, we are all a quantum field, a set of quantum fields. So why people are studying particle physics at all? So there are just fundamental questions. Which fields actually fill the universe? What are their quanta, which means what are particles, what we call in simple language particles, and how these particles or quanta or fields in general interact. And there are basically two different methods how to attack these problems. One set of methods is purely theoretical. You construct a theory which should be based on quantum field theory, which should exploit some symmetries, some conservation laws, and so all this theoretical fancy language. And another method is the experimental. So it's particle accelerators, detectors, and data analysis. So you collide different particles in the collider, and you see what is produced, with which rates, with which directions they go. So these two animations or pictures just shows typical way how these two different worlds work together. And so then all these pictures are transferred to fundamental equations and numbers. What are the experimental pillars which are behind the standard model? There is actually a large number of that, but because I'm kind of limited in time, so I just made a pre-selection. Maybe it is not something with which everyone will agree, but this is as far as I see it. So I think a fundamental thing, the first fundamental step was the discovery of positron. So people realized that for a particle, it can exist an antiparticle. And antiparticles are actually mandatory in relativistic quantum field theory. And therefore, people moved from quantum mechanics to quantum field theory. Then it was a very interesting, long-standing saga about beta decay and apparent energy violation in beta decay, which was then manifested itself is in a discovery of a neutrino and a new type of interaction, weak interaction. And so humanity discovered lepton sector, that it is richer, and there should exist also neutrino. And then weak interactions entered the theory. Another important step was discovery of parity violation, that interactions in our world and mirrored are different or could be different. This is nowadays, I think, is a kind of very natural idea to everyone. For physicists at that time, this was a very shocking idea. So many very prominent physicists did not believe that this could happen, but this is actually what happens in nature. Then the discovery of strange particles indicated that there are more than just up and down quarks. So there are other quarks, and people began to construct different classifications. And finally, after all this mathematical treatment, they discovered a theory of strong interactions. Deep and elastic scattering. So this is not just a single experiment. So this was a large experimental program which finally discovered that protons are made of quarks and gluons. And later on, weak interactions were discovered already after the standard model was formulated. And this was really a great success because the standard model predicted the existence of weak neutral interaction, and then it was discovered experimentally. Experiments with hadron jets and especially with free jets events discovered a gluon, existence of a gluon. Because already in 70s or 80s, many even prominent physicists believed that QCD, modern theory for strong interactions, was just a mathematical tool, and all the particles, quarks and gluon, are so strange that they don't exist. This is just a mathematical artifact. But after this experiment, I think everyone gradually agreed that these are real particles which do exist. Later, W and Z bosons were directly discovered, not just as a trace for the weak interactions. Then top, and finally, Higgs boson was discovered. So Higgs boson discovery was made just very recently in 2012, if I'm not mistaken. And this is, in my opinion, is really one of the greatest discoveries in the history of particle physics, because for many experimentalists, Higgs boson, I would say practically, was not needed. So this was just a particle about which theorists believe that this is needed, because standard model cannot work without Higgs boson. But for experimentalists, no observable actually was that much sensitive to the existence of Higgs boson. And this story lasted for 4 decades. And after 4 decades, this really clever, genius theoretical idea was finally proven to be right experimentally. And this is why I think that this discovery is that important. Now let's go to the interactions part of my lecture. So how do we describe the interactions? So there is a theoretical language for that. If you write the Lagrangian, then, and if you know how to manipulate with the Lagrangian, then you know everything. And the trick is that you have to learn how to manipulate. And the second, what is more difficult trick, is how to write the Lagrangian. So, but one thing you can say for sure, that Lagrangian consists of 2 parts. One is the no interaction, and second part is the interaction. And so regarding the interaction, we are very lucky regarding the electromagnetic interactions, because thanks to James Maxwell, classical theory was already constructed, and this was a relatively easy step how to generalize this to the quantum world. But already at this point, I want to highlight that the very important and very non-trivial question is how you can construct a theory for which you don't have any classical analogy. And these are strong interaction theory or weak interaction theory or something else. So anyway, for the electromagnetic interaction, the interaction Lagrangian is very simple. So it consists of a product of fermionic current and electromagnetic field. I don't invite you to dive into this equation, but what I want to stress is this cartoon, because this is a very clever and very maybe non-intuitive idea. It was kind of invented by Yukawa, but also many other people contributed to this, so I cannot really attribute who was the first. So what is this idea? Quantum field theory describes the way why 2 electrons interact as exchange of quantum of electromagnetic field. Let me put this to the extreme. If you just take a theory with 2 electrons without electromagnetic field, then they just pass through each other do not feel in each other, so they just pass through each other without any interaction. So you have to have another field which transfers this interaction from one electron to another electron. And we all know that the force, if we talk to this in this classical language, the electromagnetic force is inversely proportional to the distance squared, right? But this is valid only in 3 dimensions. If you understand the physics behind, and so you understand that the reason why there is a force is the exchange of photon, then it is a very trivial exercise to calculate this force in any dimension, like 1 dimension, 2 dimensions, 3 dimensions. And what you will realize is that if you have 2 dimensions, then the force will be inversely proportional to the distance, not distance squared. If you have 1 spatial dimension, then the force will be just constant, irrespectively of the distance. So whatever distance between 2 charges, they will have the same force. So when we were kids, I'm sure that you were solving different electromagnetic topics, and the teachers were proposing you to consider one-dimensional situation and calculate force, assuming the force is 1 over r squared. It is fine as a simplification, but you should be aware that actually, if you take this literally, then force will be different. But I think this would be too much. Okay, so how we describe these interactions in quantum field theory? This is described by these animations, or these cartoons. So this is an animation of a Feynman diagram. When 2 electrons interact with each other, as I said earlier, they just exchange by a gamma quantum. So here, on this diagram, on the horizontal axis, I show time, and on the vertical axis, I'm showing distance. So 2 electrons approach to each other, then they exchange a gamma quantum, and then they go apart. And for each of these diagrams, you can write just a mathematical equation, how you just literally transform this picture into an equation and get some analytical or numerical result for the force or whatsoever, what you want to do. And this very introductory introduction, I'm not going to show all these equations. So another force is due to the weak interactions when, say, a muon neutrino interacts with muon and goes again to muon neutrino and muon. Then you have a very similar diagram. The only difference is that instead of electrons, you have muon neutrino on top of this diagram and electron or muon on the bottom, and in between you have a Z boson exchange. And again, you have simple rules how to translate this diagram into an equation. But weak interaction is particular in the sense that it has another set of bosons, which are charged bosons. And you can now have an exchange of this charged boson, and this makes something different. Now, a muon neutrino, if you see this carefully, is transformed into a muon in the same vertex, emitting a W boson. And then this W boson is absorbed by an electron and transferred to an electron neutrino. So you see, the weak interaction is the only interaction we know which can transfer the particles, type of the particles. So all other interactions, strong and electromagnetic, they keep the particles untouched in terms of their nature. And last interaction is the strong interaction. So strong interaction, first let's look on the right diagram so that you don't get lost. So it describes the interaction between quarks. So how it is done. A quark can have, no, not can, it has a color. Here I literally draw it as a red color. And a red colored quark can interact with blue colored quark in the following way. It emits a gluon which has a red color and anti-blue color. Anti-blue color is actually yellow. Therefore, this gluon has 2 colors, red and yellow, which is red and anti-blue. When it emits this colored gluon, the red quark transforms into the blue quark. And when this red anti-blue is being absorbed by blue quark, it transforms into a red quark. And this is the way how quarks exchange these gluons and they interact. A difficulty is that this seems quite simple. But the difficulty is that gluons also do interact between each other. Therefore, this theory is very nonlinear. And this is very different theory in the end with respect to electromagnetic and weak interaction. And now, finally, we can look on another animation. So I don't know if you can realize what is jumping back and forth. So these are polar bears. Why polar bears? The strong interaction, and this is, by the way, another cartoon drawn by Marina. Now I see Marina. Can you stand up, please, that everyone enjoys your beautiful artist work? Yes. Thank you. So if these are two quarks, these two blue balls, these are two quarks, and if you imagine gluons between them as just a spring, and you want to estimate what is the force of this spring, you just put some weight in order to have the same force which acts between two quarks. And this force is equivalent to the weight of 40 polar bears. So this is the energy which is stored inside every proton of every atom, of every molecule in your body. And this is the reason why atomic electrostations are so powerful, because nuclear energy is really very, very strong. So inside of each of us, we have this much of energy. I think this is kind of useful when we transfer these abstract ideas into the simple world. And if you calculate the number of bears, I think it should be 40, right, Marina? Or about 40. 35. Okay, you calculated that. Very good. Some of them may be hidden. And so in the last part of my lecture, I'm going to tell you about Retherford scattering. So, okay, I will just make a hand waving then. What this experiment was about. They used actually two postdocs of Rutherford were doing this experiment, Marsden and Geiger, or Heiger. And they were just using alpha particles from a decay of some nuclear source, which were hitting a very thin gold foil. And normally what one would expect that this heavy alpha particle should just go through maybe deflected by a very, very small angle. But what they discovered is that in some fraction of events, quite sizable fraction of events, this alpha particle will backscatter by some 180, 150 degrees. And this is impossible to understand if you assume that atom is made of a homogeneously distributed charge. If you make the calculation, you will realize that this is simply impossible. So it is possible in principle, but not numerically. So you cannot get this observed rate of the number of backscattered events. And it took 2 years for the Retherford when he finally understood what this means. So he understood that this means that an atom is actually like a planetary system where you have inside of an atom a nucleus which is heavier than alpha particle. This is why alpha particle just scatters back, because it is lighter than the actual target. Before he was assuming, and everyone was assuming, that the charge is distributed uniformly and therefore the scattering of an elementary particle would be just scattering of a very light object. Right. And so the results showed that most of the alpha particles, passed through, and some part of them was scattered back. And this experiment actually laid down the entire field for experimental physics. So all other experiments are just kind of repeating the same exercise with larger energies, with fancier detectors, but genuinely we are doing a very simple thing. We are just disassembling our toys and trying to see what is inside, how this toy is working. So I think every kid was doing this. I was doing this when I was a kid, and unfortunately I was able to disassemble and never able to assemble back. And now we are coming to a kind of a central part of this lecture. I want to discuss with you a very simple but very fundamental problem we already can discuss. This is the problem of the Retherford cross-section. But before that, let me explain you what the cross-section is. So cross-section is a quantity which has a dimension of area and has a physical meaning of interaction probability. It is just done in this way in order to have a very convenient way, independent on the flux of a particle which is hitting your target, to describe the number of interactions. So the interaction rate, which is the number of interactions in a second, is just given by the cross-section, which is independent on the flux, multiplied by the flux. So you have 1,000 times more particles in your flux, and you have 1,000 times more the number of interactions. And so this is why we are introducing this dimensionful probability. Okay, thank you. And so when you are doing a calculation of the cross-section for the Retherford scattering, so proton plus nucleus goes to proton plus nucleus, or alpha particle instead of proton. So I'm not writing you the entire formula, but I just highlight a very important piece of that. So you will end up with either in classical theory or in quantum electrodynamics, you both end up in the differential cross-section scattering into a given angle. Remember that video where it was scattering back in a certain angle. And so the scattering to the certain angle is inversely proportional to the sine to the power 4 of this scattering angle over 2. Already here in this point, you can realize that there might be some problem, because if theta goes to 0, the cross-section goes to infinity. But you might think that, okay, maybe if you are integrating this within a solid angle, probably there is some cancellation and there is no infinity. But actually, it is not. If you are doing an integral over all possible angles, you'll get exactly infinity. And this is a big problem which has no good solution, this is not accurate, no good solution in kind of standard textbooks. So what I found in many textbooks were just hand-waving arguments, how to kind of try to deal with this or explain this. But apparently, experimentally, this is nonsense. We never measure infinitely large cross-section. We never measure infinitely large number of events. Otherwise, we would be very lucky. So we would make very small detectors and get a lot of statistics. But this is not, nature is not giving us this gift. So the experimental cross-section is actually finite. So what is the reason for this discrepancy? First reason, which is also quite rarely discussed in textbooks, is the so-called plane wave assumption. What does this mean? This means that when we are doing calculations in quantum field theory, we are very typically assuming that every particle has a very definite momentum, because then the calculations are very simple. But definite momentum, this means that particle has totally uncertain position, right? And this means that this particle is actually a plane wave occupying the entire universe. This might be okay for different cases, but here in particular, this makes a kind of a problem. Because if you replace the plane wave by a wave packet and repeat the exercise, you will realize that if you are trying to calculate the amplitude for the 0 angle, then this amplitude is not diverging. It is finite. So wave packet already treats this divergency. But there is some divergency, and this divergency appears as the phase of the matrix element. But since it is a phase, in the amplitude square, it disappears. But then you might think, okay, so wave packet is the solution to this problem. Actually, it is not. if you want to calculate the same process, but for non-zero scattering angle, you will realize that now the amplitude is going to be logarithmically divergent. This is already much better than divergence which we saw so far, 1 over theta squared. Logarithmic divergence is a kind of tolerable divergency which we can work with, but anyway, it is infinitely large. But this logarithmic divergency indicates to something important which we so far were not really looking for. Okay, so this discrepancy is softened but not removed. So the actual reason is that our calculation was assuming another thing, that there is no photons produced in this process. So you have initial proton plus nucleus, and in the final state you also have the initial proton plus the nucleus. But actually, if you just think a second about that, you will see that a charged particle going in a Coulomb field of another charged particle will make a curved trajectory like that. So it will move with some acceleration and deceleration, right? And every particle moving with acceleration must emit photons. Therefore, our initial assumption that you have the same final state is simply wrong physically. And I don't know why, from already 100 years, from one textbook to another textbook, this story is repeated with the wrong assumption that you still can have a single proton in the final state. And this is a very simple animation. You already realized that I like them. So we just see what actually happens if you just solve this carefully. So you just see that this spherical wave is a wave of photons which are produced. So this is just an exact numerical solution of this problem. So you see when you just not assuming anything but just doing a calculation, you realize that actually you have a number of photons in the final state. Therefore, we have to reformulate our problem, and we have to say that final state might or should have a certain number of gamma quanta. I think I have convinced you in that. But this is not yet a full solution. This is already, we are on the way to solve this issue, but this is not yet the final solution. The final solution is this very busy slide, but don't get scared. It's just for those of you who like formulas and otherwise would go out from my lecture unsatisfied. But I will explain you this slowly, step by step. So, as I said, exactly zero photon assumption is not valid. But experimental detector always has some finite energy resolution, which means that it cannot see energy below a certain threshold. And therefore, if some photons are produced with some small energy and your detector cannot resolve this individual energy, it just sums up all these energies. And therefore, the real quantity which we are going to observe experimentally is the following. Is cross-section where proton goes to proton with some scattering, with some modified angle, plus this part of the cross-section where you have certain number of photons where the total number of energies of this photon is below experimental threshold. And when you do the calculation, and this calculation is very difficult. So it is, I should not say that this is something easy. So this is many pages of very advanced QFT calculation. But when you do this calculation, you will end up that you are going to get this answer here. So this answer is the following. So you have some standard cross-section here times a series in the powers of alpha, which is an electromagnetic constant, with two functions, L and L mu, which are just logarithms of these quantities, where m is a mass of a proton and mu is some renormalization scale. If you are not familiar with what renormalization means, just don't think about that. So it's just some parameter. And what is bad is that this is divergent again. But now, when we understood that we can have in a detector situation when real photons are produced but their energies are nearly zero, you can get another clever idea. You can say, oh, but then I should also include in my calculations virtual photons, which also have almost zero energies and zero momenta. And these virtual photons in QFT are described even by more complicated calculations involving loops, and this is why we have this renormalization mu constant. But what is important, if you are really able to go through all these calculations, you get almost exactly function like here. It is here, but with minus sign and with the same quantity here. When you sum up these two, you get in a final answer, which is finite. So all these divergences are actually removed when you include final state with some number of photons and virtual state, which are very near to photons with zero energies. This is really a very, very complicated slide. Let me try to make it simple in simpler words. So imagine that you have a situation when a photon is produced, but the energy of photon equals to zero. Can we imagine that? So then, I hate this word, but philosophically, if there is any difference between a photon with zero energy and absence of photon. No, right? So this is the same. So actually, this means that we have already in our language some ambiguity. When energy of a particle equals to zero, when energy of the particle equals to zero, this is almost the same as there is no particle. And then in this game enters a world with these virtual particles, which pop up from a vacuum, and they also look like they have zero energies because they do not modify the final energies of a particle. Yeah, so when you sum up all this together, you get a finite cross-section, so no divergency. And this is known in QFT as an infrared divergency. To make the story very, very short, for experimentalists especially, this means very simple. This means that you just should not care at all about these infrared divergences because this is just a language issues. They are not real. They are always canceling. They are always disappearing when you just carefully formulate your physical problem. So infrared divergences cancel automatically. You just should not worry about that. There is another type of divergence which I'm not going to discuss at all. These are ultraviolet divergences. They are much more difficult, and has really physical implications and so on. But regarding this is just a language issue. But I think anyway that you have some takeaway message that already this very simple classical problem like a Rutherford cross-section has a divergency, and this divergency has a clear explanation, and when you account for it, it becomes a finite cross-section. So now let me come to my last slide. I just summarize everything which was said today. So matter is described by quantum fields, and these are the basic objects which fill the entire universe. And particles, in particle physics, these are quanta of these fields. And the interactions are constrained by some symmetries and charges. And many experiments really actually revealed the structure of the standard model, and now this is a very successful theory. And now the central question is, what is the standard model? I mentioned this already many, many times. So this is going to be my tomorrow's lecture. Thank you very much.
Thank you very much for brilliant lecture. Question, please? Questions?
Professor Naumov, thank you very much for your brief introduction in particle physics, and I have the following questions. You have mentioned that particle is excitation of quantum field, and my question is the following. Is any excitation of quantum field can be interpreted as a particle?
Very good question. Not any. So there are also, as I said, virtual particles. This is also an excitation of a field. So what we call particle is an excitation of a field when energy of this excitation is above the mass of the particle. So this is the exact formulation, what we call particle. If energy is below, then this is a virtual particle.
Okay, thank you.
Okay, thank you for your lecture again. And may I ask two questions about the last topic you talked about? You said that infrared divergences always cancel out. However, maybe I've just missed that, but is it possible to briefly explain how to characterize infrared divergences so that one knows that this is actually an infrared divergence and I do not need to worry about it and it will cancel itself out?
Yes. So when you have some final state with particles whose energy are very close to zero, then you might have, not always, but you might have a divergence in the cross-section. If it is the case, then you should go to a virtual counterpart and include other diagrams which also have this almost zero energies final state, which are virtual now. And then this divergence will cancel out. If you meet this problem in your calculation, then just this is the indication that you just miss some of the diagrams you have to include.
And I think, as for me, the way you talked about virtual particles on the last slides, it seemed like they were just a way to, like, somehow mathematically account for the fact that we, for example, do not observe all the photons, but just with some energies above the resolution of the detector. So I'm just curious how this virtual particle formalism came about and what it actually physically represents.
Yeah. Probably this is kind of your first time you hear about quantum field theory, right? Yeah. So I probably made a little bit wrong impression on you. So virtual particles are not some special construct which we invent in order to cure some problems of the Retherford cross-section. This is a very strict consequence of QFT. It is shown here on this diagram. So this intermediate particle is a virtual particle. So the definition of a virtual particle is very simple. This is a particle which is not in the initial state and not in the final state, but is present in the diagram. So it is a very firm prediction of QFT. So virtual particles do exist, and otherwise we cannot explain any interaction. So the interaction is due to the virtual particles.
So it's like some excitations of the fields?
Yes, it is. Like another guy before you asked me about types of excitation. So this is an excitation with energy below the mass of this particle. So this does not mean, for example, the W boson, which is shown here, cannot exist as a real particle. If you give enough energy to W boson, it can go just as a real particle until it decays. Or a photon, it can be a virtual particle when it is an exchanged particle between two electrons, but it can be a real particle when it just, light around us. These are just real particle photons.
Okay, thank you a lot.
Thank you for your introduction lecture. I have two questions. The first is regarding to strong interactions. You have just explained the interaction between two quarks, like anti-blue. What does it mean, yellow, the virtual gluon? I just...
Yes, anti-blue color is yellow.
Could you show it on the diagram?
Yes. I think maybe it's another way. Yes, here. If you're painting, if you paint a blue color, and then you want to make it white, you should put yellow, and yellow plus blue will give you white in the end if you put them in the current amounts. This is why it is called anti-color.
Thank you. And the second question is, I know now what ultra-red,
Ultra-red,
yes,
infrared.
divergence is, but I couldn't get what is actually the ultraviolet divergence. Could you briefly explain?
Yes, we unfortunately did not have enough time to study this subject in our class. So ultraviolet divergences are divergences which appear in so-called loop diagrams. I think you remember I was drawing from time to time these loop diagrams. And when momentum in this loop goes to infinity. This is called, because you see, if you take a wave, just a wave, and then if you want to make a low energy of this wave, you just go outside of that, right? So you like a Doppler effect. And then it is becoming red-shifted. So the length of the wave becomes longer and longer, and the energy is lower and lower. If you go to the same direction, then it is going so-called blue-shifted. And extreme of the blue shifting is violet. Violet is more blue than typical blue, and ultraviolet is even more blue than just the blue. Therefore, if you go to high and high energies, this is just a language from old times that this is ultraviolet. Just to make a connection with the usual picture. Red is low energy, blue and violet and ultraviolet, these are very high energies. And the diagrams diverge in these high energies. This is why it is called ultraviolet.
Other questions?
Thank you. I also have two questions, and the first one about standard model. I think all of us see the picture of the structure of standard model, but I think that only argument to group neutrinos and other leptons in one group of leptons is that they interact via weak forces. But maybe it is quite old point of view, and maybe it is more correct to separate these parts, I mean neutrinos and other leptons, because, for example, they have at least different mechanism of mass productions, and also neutrinos don't interact via electromagnetic force. So what do you think about this?
If I got your question right, you are kind of arguing that we should not probably place them in doublets, but in some other structure, right?
Yes, two group neutrinos and
kind of singlets for neutrino and singlet for electron.
Yes, maybe something like this.
Okay. Yeah. This is certainly possible, and certainly you will not get this way the standard model. You will get some other theory, which most likely will be in conflict with observational data. So why Weinberg and other guys placed them in doublets? The primary reason was experimental discovery, as I said, of the parity violation, that weak interaction violate parity. Then another great experiment, which I did not mention here, was experiment which actually measured the orientation of neutrino spin with regards of its momentum. This is called spirality. It was found that spin of neutrino directs always in the opposite direction to its momentum. This is left-handed particle. And then tomorrow I'm going to say more about standard model, but now I can kind of explain this already. And then another thing is that in order to explain both electromagnetic interaction and weak interactions, you have to have at least 4 force carriers. 4. We now know them as W plus minus Z and gamma. And then you just begin to look for groups which can form so-called generators. So this is just a mathematical point of view. And you take the first group, which is U1, it has just single generator. You take SU2, it has 3 generators, not enough. You take SU3, it has 8 generators. This is already too much. And therefore, you just say, okay, it must be a product of SU2 and U1, 3 from SU2 and 1 from U1. And then you get exactly 4 force carriers. And once you have this SU2 in this game, then its representation are just doublets. So it is very natural to place them in doublets because now these particles are going to interact with these force carriers. So this is simple idea behind.
Okay, thank you.
But you are right, in principle, one can create a more complicated theory with much more parameters. But certainly, fathers of the standard model wanted to create as much simple theory as possible, and it turns out that just this theory is working.
Okay. And another question, you said that without electromagnetic interactions, for example, if we have 2 electrons, they
Do not interact.
yes,
Mm-hmm.
goes one through another.
Right.
Let's imagine that we have 2 electrons with the same spin and in
Right.
points. And if I trying to push one to another, I think that we have Pauli principle.
Yes.
And I going to feel something like that these electrons are repelling. So what's the situation?
Very good question. So it is certainly a good candidate for awarding cat. Yes. On purpose, I did not mention this effect. This effect really exists. And you are completely right. 2 electrons, when they overlap, even without any photon, they are going to feel a certain force due to the Pauli repulsion. It is not that force which we are typically talking about, like what we call gauge force. But this is going to be really like a force. And you can make even a calculation. So on a YouTube video, there is a lecture where I'm just explaining this. So you can make a calculation and you can actually see this directly in the scattering of 2 electrons. You can see the impact of this force on the final amplitude. So it is really the effect. So in this regard, you're completely right.
Very interesting.
Yes, yes.
I have maybe a little bit naive questions. Your lecture remind me British hospital. When you are not dying, you don't treat it. It means if you have not wrong results, you don't continue to investigate it. Like when you should stop treatment of your results, when you should find the proper solution, where is the limit, correct limit?
Can you reformulate your question in a more simple way? I am, as a patient in the hospital, already has some difficulties to understand it.
When you have like a not absorbed results, you say it's correct. If you get infinite cross-section, you start to think. You start to find the solution.
Mm-hmm.
and go to the point when you get not infinite result.
Yes,
But why it's correct result?
you're right. Yeah, now I get your point. So everyone understood the question? Yes? Okay. I was just the last one. Yeah, so very good question. But this has nothing to do with my lecture or QFT or whatever. This is just a scientific research, right? So if you are obtaining a result which looks reasonable and you stop investigating, then it might be wrong, right? If you just get immediately wrong result, then you must investigate what is going wrong. So this just about a different dimension of our work, that we must be very critical in first place to our own result. We must attack it from really different angles, and not just a nicely looking result. Especially I want to explain this to students because you have a great pressure from your professor classes. You have to pass a lot of homework and so on. And after a few years of study, the main principle is to pass this homework, right? So if you pass the homework, then you don't care about anything. But then when you enter a real scientific work, passing means nothing because who cares what you just pass? You have to make a right analysis, publish a defendable paper, right? And so if it is not defendable, so no point. You do not pass it to anyone. And so there is some kind of a psychological change. And I think this question is just remind me that we must make it as early as possible. We must be very critical to ourselves and always try to find mistakes, even in correctly seeming results. Are you okay with this?
I mean, like, why you will stop to use like virtual particles for first results when you have like a correct one? Just single first order diagram, second order, and second.
So why I'm okay when I get the final and I'm not investigating more, right? Actually, this is not me. So this is a very long, for many decades story. And I would say that theorists of all the generations, like if they are 70 years old, something like that, they sometimes do not know that, for example, infrared divergency is already gone from QED. Because when they were young, this was yet an active field of research. But now, after many decades, we think that the subject is sorted out. Maybe we are wrong, but at least we stop here because everything seems to be very self-consistent.
So I would like to comment your first question. I think I understand what you mean. The situation, I call it the dark theorem. For example, we have an animal. We define it to be a duck, some salient features of this animal. And in the street, we see an animal, it quacks like a duck, it walks like a duck, then we think it's probably a duck. Then we take it home, and it grows, and it finally produces a very big egg. So we realize we are wrong. It's a goose, it's not a duck. So in physics, we simply modify our dark theorem to describe a goose properties. So in this sense, physics is not mathematics. From the beginning, we simply do something we can observe and we can test. And finally, if we find something wrong, then we make modifications.
Do you agree?
Sure.
More questions? We have time.
Can you show your slide with two formulas for the cross section with real and virtual contribution? And my question is it if you can quickly to explain both this answer on the language of Feynman diagram, to draw what is the difference of the Feynman diagrams for the real and for the virtual photos.
How Feynman diagrams look?
Yes.
So the first one,
Maybe you take the door and
so this is the tree diagram with gamma, which makes the cross-section divergent. This is the one diagram. Then you should add to these diagrams, to this diagram, another one, another type of diagrams where one of these or that emit a real photon. It can be here, it can be here, and actually you have to sum up all these kind of diagrams, single photon, two photons, and so on. This is not yet.
for the first.
This is for the first one.
In what order?
Yes. And what is the other one is that you have this kind of diagrams, virtual, and all possible other virtualities like that. The point is that when the virtuality of this photon goes,
And something like this.
yes, like a ladder, yes.
Like a ladder between two legs.
Yes, between two legs, yes,
Okay.
all possible. And when the virtuality goes to 0, then you will see here when Q is 0, then the logarithm becomes infinitely large and you get again infinite cross-section. But then it turns out then when you sum up these types of diagrams with these plus this type of diagrams, then these logarithmic divergences disappear magically exactly.
You said about maybe as I remember, the Kinoshita-Lee-Naumov theorem about the cancellation of all infrared diagram, yes?
I think it has another name. Yes, I think it has another name, but there is the theorem about cancellation of infrared
divergences.
of infrared divergences, right?
Okay, thank you.
Mm-hmm.